Hello and welcome back. In this video, we're talking about functions of three variables and their partial derivatives. So this is following a theme where I show you how things work for functions of two variables, and then things more or less extend naturally to three or more variables. So here we'll just go through an example of finding partial derivatives with respect to x, y, and z now, because here we have a function of three variables. We'll find each of these partial derivatives. So nothing really changes in the computation, only now I have three variables, so if I'm differentiating with respect to x, that means I'm going to keep y constant and I'm going to keep z constant. That in x's eyes, y and z are constants. So let's differentiate this with respect to x. One thing I can notice here, cosine z in the eyes of x is constant, so that's just a constant. And then I have e to the minus xy. So there I have y times x, and it's negative, so I'll have a chain rule there. But that should be it. I won't have to use a product rule because, again, cosine z is a constant. So just before I start differentiating, I want to develop a sort of strategy, get an idea of what kind of derivative rules I'm going to be using. Right, so here it looks like it's going to be a chain rule with this e. So derivative with respect to x. So the derivative of the inside here would be minus y. So I'll have minus y, and then the derivative of the outside, well, it's e to something, so that'll be e to the inside, minus xy. So there's, and then don't forget this constant that's hanging around, cosine of z. Constant with respect to x, that is. So there's the partial with respect to x. Let's go ahead and find our partial with respect to y. Again, locate where are my y's in the function? Well, they're just here inside of the e, just like x was. So this is going to look very similar to f sub x. Instead, this negative x is going to pop out because it's the constant multiple of y. So this will be negative x e to the minus xy. Cosine z comes along as a constant with respect to y. All right, finally, let's find the partial with respect to z. Again, find out where all my z's are. Oh, it's just in cosine. It's just in this cosine function. So this e to the minus xy, that's just a constant that's coming along for the ride. So I'll have e to the minus xy times the derivative of cosine z. That'll be minus sine of z. So maybe I'll take one rewrite of this and bring that negative to the outside. And there we have it, the three first-order partial derivatives of f. Now again, we could differentiate each of these. Right now, each of these is a function of three variables, right? So that means we can take partials with respect to x, y, and z. And so we can have second order. How many of those would there be? Well, there'd be 3 for this one, 3 for this one, and 3 for this one. So that'd be 3 times 3, or 9. So a function of three variables would have 9 second-order partials. But Clairaut's theorem is going to come in and help us again and tell us that, well, some of those are going to pair off, or rather triple off, and be equal to each other. That is the mixed partials. So for example, fxy. So this function is continuous on the entire in all of space, and so for instance we would know off the bat, if I took a derivative, these would also be continuous. That fxy equals fyx, fxz would be equal to fzx, and so on. All right. That's it for this video. In the next one, we're going to work some examples, some real-world sort of applications of partial derivatives in the context of temperature, pressure, and volume. We'll use the ideal gas law for that. I'll see you there.